Hi, in this video you're going to be building a fully connected neural network completely from scratch using only Python and NumPy. We will discuss the forward pass, backpropagation, and the flow of computations through the network. The only prerequisite is that you have a good understanding of matrix multiplication as well as multivariate calculus, including the chain rule. By the end of the video, you will discover that once you understand the different mathematical operations, implementing the code is actually the easy part. Once we're done, if you think that this video has been useful to you, please don't forget to comment and like and share it with someone that you think might be interested in understanding the different mechanics of a neural network. So at its core, a neural network is a function approximator. It maps an input x to an output z out, and it achieves that by passing the input through a series of transformations, and these transformations depend on these learnable parameters. These are the w's and the b's in our diagram. And the goal here is to tune these parameters such that the output is as close as possible to the true labels. So if we have this data set, our input is an x coordinate, and our true labels are this y coordinate, and our function wants to predict the line that fits through the data points. This is our z out. And it does that by using an objective function. The purpose of this objective function is to propagate information back into the network that tells these parameters how much they need to change and in which direction. So for example, here we're using a regression problem. We're trying to fit a line through the data. For that we use mean squared error, which is an appropriate loss function. And the way it looks is as follows. This is our loss axis, L. This is our L function. And in terms of z out, it is raised to the power 2, so it is a parabola. And the goal is to minimize the loss and find the z out that achieves that minimization goal. Okay, so this is optimal z out. This is a z out axis. Okay, and the way we do that is by computing the gradient, or the first order derivative between L and z out, and that derivative gives us the direction that points towards the optimal value of L. Okay, so we start from a random place because we don't yet know our parameters. Okay, and we compute the gradient, and it tells us which direction we need to take. We take a small step in that direction, we end up in another point here. We compute the gradient again, we end up in another point here. We keep doing that until we get to a point where our gradient is horizontal, and then we know that we achieved the minimum loss. So by minimizing the loss, we make sure that z out is as close as possible to the true labels. Okay, now the issue here is that z out is not a tunable parameter. So even if we computed this gradient, we can't go to z out and ask it to update itself, because z out is made out of multiple layers of transformations. So what we want to tune is buried deep inside z out. The first one is right within z out. We have these tunable parameters, but then we need to get to these. So we need to go to u2 and then get to z2 in order to tune these parameters. So the way we do that is by using the chain rule. So if we look at our function here, okay, let's start from a parameter that we want to compute the derivative with respect to. Okay, let's pick w2. All right, w2 is a parameter within z2, right? So we have z2 is written in terms of w2, and then z2 is fed to u2. We have u2. Then u2 is fed to who? It's fed to z out. And then finally, z out is fed to our loss function. So our loss is written in terms of z out. So here we want to compute dl with respect to dw2, dw2. Okay, and the way we do it is we compute derivative of L with respect to z out, multiply by derivative of z out with respect to u2, and then we keep doing that until we get to the parameter that we wish to tune. Okay, so what this states is that dl dw2 is equal to dl dz out, dl dz out, multiplied by dz out du2, dz out du2, multiplied by du2 dz2, du2 dz2, and finally it's multiplied by dz2 dw2, which is the parameter that we wish to get to. So this is w2. And to confirm that your chain rule is conceptually correct, you can look at these as fractions, just conceptually, and you can cancel out z out with z out, u2 with u2, dz out is 2 with dz2, and you are left with dw2 and dl. And that is exactly what we are looking for. So by computing the derivative of L with respect to each one of these tunable parameters, we can go to these parameters. So now we can go to W2 and we can tell it, hey, we have information from the loss function, and this information will give you the direction in which, if you move towards, the output Z out is going to be better the next time we run the data through the network. So this is DL, DW2. W2 is going to take it, and it's going to take a small step because we don't want to take the full gradient. If the gradient is too large, it might, and I update my W with the full magnitude of the gradient, it might end up on the other side of the optimal value, and we will end up just going back and forth without ever converging to this value. So we take a small step typically, and this step is called learning rate. Now there's a small issue here. When I said that this gradient points towards the optimal value, I actually lied. A gradient points in the other direction of the optimal value. This is the gradient. This vector is the negative of the gradient. Okay, so what you want to do here is you want to add the negative of the gradient. Okay, we want to add the negative of the gradient, and with that we have the what they call gradient descent. Okay, this is gradient descent because we are using the gradient to descend through the loss landscape. Okay, so that is the full cycle of the data that goes through a fully connected neural network. We have our forward pass, we get to our loss, we compute it, we compute the gradient, and then we propagate it back through the network by hopping from one layer to another. We hop, we compute the local gradient of that layer, and then we take it and then we move to the next one. Now, let's have a look at exactly how our forward pass is processed. So this is a typical feed-forward layer, okay? It's a hidden layer. It consists of two components. The first one is linear combination or linear mapping, and the second one is nonlinear activation. Let's say, for example, our dataset is a one-dimensional dataset, so our dataset is X, okay? And it consists of X1 all the way. Let's say we have 10 data points, 10 of these points here, okay? All the way to X10. We represent it typically by a matrix notation, okay? So we represent it this way. So this is a 10 by 1 matrix, 10 entries, 10 separate data points, and a single dimension. Each data point is represented by a single X value, okay? What we want to do is, when we say we are applying linear transformation, is this single dimensional space is too small or too limited for the network to learn these nonlinear relationships. We want to give it a higher capacity to learn. So we map it using a transformation matrix, W. This is the W matrix. It is a transformation matrix. It maps the input from the dimension it has. So it is, this W matrix is 1 by to the desired output. So we want to map our input to 3-dimensional space. So here we have 3 nodes. It means we are mapping our input to a 3-dimensional space. So that means our W has 3 columns. Okay. What this does is it gives us Z, which has a dimension of 10. Sorry, when I said dimension, I meant the number of rows. Okay, and it has a number of columns of 3. So our input was transformed from 10 data points, each having a single dimension, to the same 10 data points, but this time each one is mapped to a 3-dimensional space, okay? As I said, this gives the network a higher capacity to learn. So whenever you see a matrix multiplied by another matrix, what you want to think of is our first matrix. So this is a dot product. When we say multiply, I meant dot product between the two. So you want to look at this matrix as a set or a stack of vectors. So this is our vector, first vector, this is our second vector, and this is our 10th vector, okay? And by applying this transformation to our set of vectors, okay, each one of these separate independent vectors are transformed into another set of independent and separate vectors, but each one of them, instead of having a single dimension, is having 3 dimensions, okay? That's the whole idea behind this linear transformation. Okay, after we perform the transformation, we need to apply a very crucial step in a neural network. Actually, without this step, this line, we can never predict. The nonlinear activation, here we are using a sigmoid function. Its main goal is to allow the network to find these bends in your data. So if your data is not a straight line, and you need to fit your line through these bendy data points, you need to apply this activation. Here we're using a sigmoid function. A sigmoid is sigmoid of x is equal to 1 divided by 1 plus e to the minus x. And how it looks is it has an S shape. It has a shape like this, okay? And it is bounded by 0 and 1. This is the x-axis. And this is 1, and this is 0. So any number you put through a sigmoid function, you put 100, you put minus 100, you put a million, it's going to be, the output is going to be bounded between 0 and 1. So all you can get is 0 and 1, a number between the two, okay? This is exactly what happens inside a hidden layer. This is the full process, okay? Now, because here we are using a single layer, okay, the next step is to get this output, okay? So this output is, again, it needs to conform to the output of the desired output of the network. So since we have a single y that we need to predict, this output needs to map our 3-dimensional data back to the 1-dimensional space, okay? Before we do that, we need to use our activation matrix. So this is taking these 10 by 3 points and is squishing them into another matrix of 10 by 3. It's just the values are going to be squished between 0 and 1. Okay. Now we want to transform this from the 3-dimensional space down to the 1-dimensional space. We use exactly the same process here, except it's in reverse. So we have W out takes 3-dimensional space and maps it to 1-dimensional space. And this gives us our Z out. Z out has a shape 10 and 1. Okay, so we have 10 data points. Each one of these 10 data points have a corresponding value in the output layer. Okay, and our loss has also again the same shape as Z out. So it's our L is 10 by 1. Now this is the full process that we need in order to implement a fully connected neural network in Python. Now before we move and go to implement the code, let's have a look at what happens when our network does not have an activation, okay? Because this is a crucial step. So here I modeled our network. We have 3 linear functions with tunable parameters. These are the A's and the B's. And after that, I put them through 3 sigmoid functions. These are activations, okay? So this has the M, N, and L. M, N, and L are our linear functions. And then finally, I combined them together. And I gave them also weights. These are the U, S, T, and V. What happens when we add them together? Okay, so we had 3 sigmoid functions. When you add them, you get this nonlinear shape. And let's change these weights, the A's and the B's. Okay, when we change them, we can change the shape of the output. This is exactly what our neural network is doing. It is tuning these values to fit to the desired shape we want. These are also the weights of the final layer. Also, they can achieve more nonlinearity. Okay. Now, look what happens when we don't use a sigmoid. Okay, so here I removed the sigmoids and I added the linear functions directly. So in our diagram, I removed this and I combined these linear functions in this final output layer. This is predicting a single line, and it doesn't matter how much we tune our parameters, you will always get a single line. So a neural network that does not have an activation layer will be equivalent to a linear regression. It will be no different than linear regression. Okay, that's why neural networks are very powerful, and they can fit to almost any shape you would like them to fit to. Okay, now let's have a look at how we are going to implement the code. The way we're going to implement it is in the following manner. We're gonna have a separate object for each one of these components. So we have an object for MSE, for the linear layers, and for the activation layers. Okay, let's start with MSE. MSE is gonna be this. C is gonna take an input, and it's gonna give us an output that is the loss. Crucially, it's gonna send back a gradient. Okay, so this is back gradient. And this back gradient is computed within it. That is the DL, DZ out. Okay, now let's look at a linear object. The object of the linear layer is going to be very similar. Okay, linear. It's going to have an input, output. It's going to take a gradient from the next layer. So you can imagine if this is the Z out, it's going to take the DL, DZ out. Okay, it's going to take a gradient. And it's going to compute its own local gradient. So it's going to do DL. Notice here we denoted all the linear layers as Z. So this is DZ. And we denoted all the activations as U. So this is going to be DZ, DU. So it doesn't matter which layer it is. These could be 1, 2, 3 layers. Okay, it's always going to be a U and a Z. But the important part here is that DZ, DU is actually locally calculated. So it doesn't need information from outside its own layer to compute this. Okay, it computes that and then it multiplies it with the gradient and it sends it back. So back gradient. So if you notice here, each one of these layers is only computing a local gradient and it's multiplying it by whatever it receives from the next layer and it's sending it back to the previous layer. So similarly, we are going to implement let's copy that, copy. This is going to be our activation. Let's delete that and delete that. It's going to be exactly the same. So this is activation. And here we're going to compute DU, DZ. So that is all we're going to need in order to implement our forward pass at least. So even though we discussed the backpropagation, I'm going to go implement the forward pass in Python before we go back, because there's a crucial step. We need to discuss the dimension of these gradients. So we already discussed the dimensions of the forward pass. Okay, and that is going to allow us to go and implement the code for the forward pass. When we're done with that, we're going to come back to here, discuss the dimensions of the backward pass, and then go back to finish off our design. Let's go there. Okay, so we are going to start with our linear layer. The initialization takes in the dimensions of our layer. So we have an input dimension and an output dimension. And inside, we're going to initialize our weights. We are going to use random and NumPy.random.randn, which is a normal distribution with a mean of 0 and standard deviation of 1. And this will take our input dim and output dim. We're going to initialize our biases same way, except this time we'll, because we only have a single bias for each node, so each one of these dimensions we have one bias, so we initialize it with this. And we will need the input in the forward pass, so we initialize it here, and that's all. Now forward pass takes the input. That input could be one dimensional, so we are going to make sure it has the proper shape. Is equal to input dot reshape this one if the length of input shape I'm typing English now is equal to 1, else keep it as is. Okay, because if we don't specify the column dimensions, it might come as a single shape, and that will be problematic when we perform matrix multiplications. Okay, now inside the forward pass we return our the output of this operation. So we have x, which is input, dot w plus the betas. So we have self dot input dot, that is the dot product, self dot weights plus self dot bias. That's it. That's our linear layer. Let's define our backward and just leave it as it. Our backward, it takes a gradient, and we will just pass for now. Now we're going to copy the same one for activation. We're going to make it for a sigmoid. It doesn't have any weight initializations, doesn't take any inputs, and sorry, it doesn't have initializations. It does take an input. We're going to define that, and then we're going to have to define the sigmoid function itself. Sigmoid of x returns a 1 divided by 1 plus np dot exponential of minus x. And in the forward pass takes an input, and it returns the sigmoid. So self dot sigmoid of our input dot input. Now we will implement our loss, mean squared error, MSE. Okay, the MSE is going to take an input as well as the labels. So that is none. To remove that, and inside our forward pass we keep that. We do the same for labels. It's probably not required because we are not going to perform matrix multiplications with a label, but it's not going to hurt. Labels, 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 labels. Okay, and we will return the loss. So np.mean of, that's a single scalar value for the whole batch. Mean of, we calculate it here, self.input minus self.labels, raise it to the power 2. Okay, now that's it. We are done with the forward pass. I'm going to quickly prepare a data set and then build a network and then come back to you. Okay, so I prepared this data set, the x from -3 to 4, and it is a parabola, so I just squared, that's the y values, labels, just squared values of the input, okay? And I built this network exactly how we discussed it. So initialize our layers, so I made it a 2-layer network. It takes an input 1, and it projects it to 64 dimensions, and then I added another layer with the same dimensions. It doesn't change the dimensionality of the input. Both of them are followed by a sigmoid, and the final output layer takes it from 64 down to a single output. Okay, and I put them in the forward pass. So the forward pass takes the input, activates it, and then projects it, activates it again, and then that is our Z out. It's another linear layer. These are incorrect labels. This is 2 and this is 2, and Z out is actually Z out. Okay, that is our network. Now, so Z1, A1, Z2, A2, that's all correct. Now here we're going to initialize our loss criterion. We're going to call it criterion equals MSE, and our model is equal NN. Okay, let's run all of these, no problem so far. Z out is equal to NN.forward, and then let's give it our input X. We have an error, so our forward, oh, because it's model, not NN, right? But still we got, oh, model NN. Is it initialized? It is, yeah. Oh, it has no attribute Z1. That's interesting. Oh, we are missing an underscore. Okay, let's see. And we got it. So this is Z out. Let's have a look. So our Z out should be 64. Oh, no, it should be just a few labels. Why is it not printing? Print Z out. None. Isn't that interesting? So that is our NumPy array, because we are not returning our Z out. Okay, so this is the outputs. Our forward pass has passed. These are the outputs. They don't make any sense because the weights are initialized at random, and we are not optimizing it yet. We are not doing the backpropagation and this whole process. So now let's move to discussing the backprop part. Okay, so in the backprop, we are going to focus on the loss, the linear layer at the output, and the activation layer. We won't be too concerned with this because this is just, as long as we fix it for that, this is just going to be a repetition of this one. Okay, so we're going to keep our operations within these 3 layers. Okay, the first thing is we need to consider which derivatives we need. So we do need DL, DZ out, okay, to get to anywhere in the network. So that is the first one. Let's put it here. DL, DZ out. And then we need DZ out, DU to get back to the activation layer. Okay, so that is DZ out, DU. We're going to need that. And then within the linear layer, or any linear layer, so we want the DZ. Okay, so to update the weights, we need the DZ out, DW. Okay, DZ out, DZ out, DW out. Okay, and DZ out, DB. All right, we're going to put it next to this one when we finish it. Let's start with this one. This one is simple. DL, DZ out is 2 times Z out minus Y true. It is 2 times Z out minus Y true. Okay, we're going to leave the N for now. We're going to put it, when we implement it, we're going to add it. But there's a bit of a nuance to it, so I need to explain what exactly we're gonna do with it. So I'm going to leave out the summation and the N, okay, for now. DZ out, DU is nothing but W. So this gives us the W matrix, okay? In this case, it's the output linear layer, so it's W out. And the DZ out, DW out is nothing but the U matrix. So this is U, and DZ out with respect to the bias is, or bias out, is equal to 1, or a vector of 1s, or a matrix. Okay, we're gonna just use 1. Okay, these are the derivatives. Now, what are the actual we do need one more derivative. When we get to the activation, we need to calculate the gradient and send it back. Okay, so within the activation itself, we need du dz, which is the derivative of a sigmoid. Now, a sigmoid, let's write the sigmoid, let's call it s. S is equal to, let's write it in this way, 1 plus e to the minus x raised to the power minus 1, okay? The derivative of that would be ds dx would be minus 1 plus e to the minus x to the power minus 2 multiplied by the derivative inside the bracket, which is minus e to the minus x, okay? This is equal to, the minus cancel out, so e to the minus x divided by 1 plus e to the minus x to the power 2. We can do a trick. We can subtract 1 and add 1, okay? And put this between two brackets. This will be equal to these two terms, 1 plus e to the minus x divided by 1 plus e to the minus x to the power 2 minus 1 divided by 1 plus e to the minus x to the power 2. This is sigmoid squared. And this cancels out with this, and this becomes sigmoid, okay? So the derivative is equal to sigmoid multiplied by 1 minus sigmoid. That's what we need here. This is equal to u times 1 minus u. These are all the derivatives that we need, okay? Now, let's discuss the shapes of the derivatives, okay? Because we need, in the chain rule, we're going to need to multiply them together. So we calculate it in the loss, we send it to z out. Inside z out, we need to calculate this and multiply it with this. But the shapes can be tricky, all right? So let's discuss what these shapes are and how we can think about them, all right? So the dl dz out is a 10 by 1 matrix, right? Because it's written in terms of z out. So it's a 10 by 1. Let's use blue for that. Let's use green, actually. That's green, yeah. It's 10 by 1 matrix, all right? This will have to be sent back to z out. And within z out, what we need to send back to u is the gradient of z out with respect to u multiplied by dl dz out. And that is dz out du, okay, which is the w matrix. So the w out matrix is 3 by 1, okay? So this is 3 by 1. And that, the product, when any gradient we want to send back to the previous layer, we need to make sure its shape conforms to the shape of the output of the previous layer. So the shape, when we multiply these together, the output shape will need to conform to the shape of u. U is 10 by 3. So we're trying to multiply a 10 by 1 with another 3 by 1. And we wish for the outcome to be 10 by 3. Now, you can think about it in this way and then arrange your terms in that manner. So we can say what we need to send back, okay, inside of z, what we need to send back is, so we need this 10 to the left. So it is dl dz out dot, we perform a dot product with the transpose of dz out du, because we want the 3 to be on the other side and we want the 1 to be in the inside, so the 2 can be multiplied, okay? So what we need to send back here in the linear layer, what we need to send back is dl dz out, dl dz out, okay, that's a 10 to the left, dot the transpose of dz out du, dz out du transpose, okay? That is the gradient we need to send from the linear layer back to the activation layer, and the gradient from the loss back to the linear is going to be just this one. It's not multiplied by anything. So this is how you can think about it if you want to think about matrix shapes. However, notice how this has the shape. Remember, we have 10 data points, so this has 10 rows, okay? So these are 10 gradients coming from the loss. Each gradient represents a single one of our data points, okay? And notice the shape of dz out du is 3 by 1, and that is the shape of our transformation matrix. So the way you could think about it is that, remember how that matrix transformed from 3-dimensional space back to 1-dimensional space, and now we had to multiply it by the transposition of this one to send the gradients back. So the way you can think about it is, I have 10 gradients. They are in the 1-dimensional space. I need to use the same operation that led from the 3-dimensional space back to the 1-dimensional space, but I want it in the opposite direction. So I want to send it from 1-dimensional space to the 3-dimensional space. And that's why I can transpose it, and this will become 1 by 3 instead of 3 by 1. So now I'm sending my gradients from, this is our 10 by 1. I'm sending my gradients from the 1-dimensional space and mapping them to the 3-dimensional space so they can have the same shape as the output of the previous layer. And now I can perform operations inside that layer using these mapped gradients. That is a more accurate and intuitive way to think about it, rather than just shapes. You want to think why these shapes are changing. Okay, now let's go and implement it and then come back to discuss the final gradient. Okay, so let's go dl dz out. That's the easiest. That's 2 times z out minus yt. Let's go and implement that here. So in the backward pass, we're going to return. Okay, we said 2 times z out, which is the input to the loss function. So self dot input. Okay, and this is between brackets. Okay, minus our y. So self dot labels. Okay, now this is the 2. What we're going to do, remember here I said we're going to leave out the n. Okay, we're going to divide by the number of data points. The reason we are doing that, and that number is the length of our input. Okay, the reason we are doing this is because you will later see how, if we don't do that, if you change the size of your batch, the number of data points within your batch, the gradients, the size of the gradients will change along with them. So what you send back to the network will be scaled by the number of data points, which is something you don't want to do, because if the gradients themselves are scaled based depending on the batch size, it means when you go and perform your when you go to update your weights, you need to adjust your learning rate. So if you started with 10 data points and then your gradient was appropriate and your 0.01 learning rate was appropriate, and then the next batch you add 100 data points. Okay, so now your gradients are 10 times larger than the previous batch, and our learning rate is no longer appropriate because you're still taking the same step, the same 0.01. Okay, but you are doing it on a vector that is 10 times bigger. So to avoid that, we scale it at the source of the backprop process. So we are backpropagating from here. We'd rather scale it here than having to scale it every time we go to update. So we could scale it within the process of updating for each layer, or we could scale it once here and then just not worry about the size of the gradient. Okay, not worry about having to change our learning rate. Okay, so that is our loss function. Our linear layer, it's going to take dl dz out, so it's going to take the gradient. Okay, dot product dz out du. Dz out du is self dot weights. Okay, and then transpose. So we're going to take gradient dot self dot weights transposed. That's all. There's nothing more to it. So we're going to have to update the weights, but let's leave that for now. Return. Okay, a gradient multiplied by dot product self dot weights dot t. We are transposing it. All right, let's leave that now, and let's go and discuss how we're going to send the gradients from here back to here. So here we have so here we receive this gradient from here. Okay, and this gradient is the multiplication of these two. So the gradient coming from here is 10 by 3. Okay, so the gradient grad is 10 by 3. Okay, and we want to multiply it by du dz. Du dz is also Actually, this is not the tricky one. I made a mistake. The tricky one is how we update it inside. I just confused the two. So this is actually very simple. All right. So here we got the du dz. Du dz is u times 1 minus u. Okay. This is written in terms of our u, and u is 10 by 3 as well. So since the activation, it did not change the shapes. Okay. So the gradient recent is simply a pointwise multiplication between this gradient it receives and this one calculated inside it. Okay, so we are going to do grad multiplied pointwise multiplication by the sigmoid times 1 minus the sigmoid. Let's do that. Sigmoid is going to return grad normal multiplication times this value. Okay, this is a sigmoid times 1 minus the sigmoid. That's all we are returning. Now, inside the linear layer, now typically when you want to update your weights, you want to have a separate method that it's usually called an optimizer that goes to the layer that has weights. It traverses the computational graph and then looks for layers that have weights, and then it updates them. For our implementation, I'm going to leave it much simpler. I'm going to update it right from within the layer itself. Okay, that's not the typical way to do it, but it's the more intuitive way to be in line with what we discussed. Okay, so we're going to have to update our weights within the backward pass of our linear layer. Okay, but let's look at the shapes. Okay, so inside here, we want to, once we get our dl dz out, we get here, we want to multiply it with dl dw out. Okay, dw out is u. U has a shape of 10 by 3. Okay, so what we're trying to multiply, we're trying to multiply 10 by 1 and 10 by 3. Notice how in every matrix multiplication we did before, we had some sort of a transformation matrix and a vector matrix. Okay, so we had something that has 10 in it that indicated that these are coming from these values correspond to our input. Okay, and another matrix that was performing a mapping from one dimension to another dimension. Okay, but in this case, what we are trying to multiply is a 10 by 1 matrix and a 10 by 3. So both of them are sets of vectors. That is a different operation. The way you want to think about this is you have these gradients with respect to z out, okay? And you want to try to access from the z out, you want to access the w's, okay? The w is your target. That is your end result. And the w is in itself a transformation matrix. So the gradients of the w are transformation gradients, if you want to think about it that way. Okay, so we're trying to access this matrix that tells us how much each weight, when we wiggle it a bit, how much it changes the loss value. Okay, and that matrix has the same shape as our w, right? Because we are going to perform like direct summation between the two, or subtraction, when we update the weight matrix. Okay, so what this is telling you, you have, let's look at our operation before. We had a vector. Let's use the red. Okay, we had vector 1. Okay, we multiplied it with vector 1. We dot product it with a transformation matrix to get a new vector. Okay, now we have a new vector. We have a vector, and we have the v1, and we want to try to figure out what kind of transformation led to. So the assumption here, you are saying, okay, one of them was transformed to the other using a transformation matrix, and the goal is to find the transformation matrix. So what we're going to do here, so what we did before was called dot product or inner product. Okay, what we're going to have to do is, when you have two sets of vectors and you want to figure out the transformation that resulted of one of them from the other, you perform an outer product. The outer product leaves the dimensions out. So if our vector is 10, let's actually take our vectors. So if this is 10 by 3, and this is 10 by 1, okay, we want to take the dimensions, that is the outer shape, okay, we want to leave these out when we want to keep them on the outside when we perform the dot product. So we want, and what's the shape of our w here? Our w is 3 by 1. So we want the 3 to be to the left and the 1 to be to the right. Okay, so we want 3 by 10 and then we want to multiply it by another vector, okay, 10 by 1. So what happened here is we have the dimension on the outside and the dimension on the outside from this side, okay? So when we perform the dot product between these two, we end up with a matrix of the shape 3 by 1. So basically, we are collapsing, we are summing the result of the dot product between the 10 data points. We are collapsing all of them. We are getting a single matrix that has a summary of our 10 data points. So how you want to think about this is we are summarizing our 10 data points in this transformation matrix. Okay, that is what the outer product does. Now, what happens if these are 100 data points? This is back to our point about scaling the loss. If these are 100 data points, okay, the output matrix is still going to be 3 by 1, but instead of summing 10 of them, we're going to have to sum 100 of them. So that leads to an increase in the magnitude of this little matrix. So this little matrix of 3 rows, okay, W1, W2, W3. These values, instead of being the result of summing 10 vectors, they're going to be the result of summing 100 vectors. So their magnitude is going to be 10 times more than the 10 vectors. And that is why we scaled at the source to make our network invariant to these changes in the batch size, okay? So now what's going to happen? We have these two sets of vectors. We want to perform an outer product between them, okay? And we want it to conform to the shape of our weight matrix, okay, which was a transformation from 3 to 1, okay? So we want the 3 to be to the outside and the 1 to be to the right side. So 3 to the left side and the 1 to the right side. So we're going to have to transpose this, okay? So it's going to be D, Z out, D, W out, transposed, dot, so this is going to be a 3 by 10, dot, DL, DZ out, DL, DZ out, which is 10 by 1. Okay, so now this cancels out with this. We end up with a 3 by 1 matrix. So DZ out, DW is U, and DL, DZ out is the gradient we received. So it's going to be U transpose. U is the input to the node, so it's going to be input transposed dot the gradient. Okay, let's go and implement it. This is going to be, so let's say self dot weight. So we're going to have to update them. Minus equal. Okay, we're going to subtract it. Let's give it a small learning rate multiplied by, as we said, it's going to be self dot input transpose dot t at gradient. That's it. That's all we have to do. Now the bias is a bit less complicated. Our bias is a vector of ones, and it's going to have to be multiplied by our gradient, and the shape, okay, the shape will need to be the same as the output shape. See what happens. It's if we have a vector of ones. If you have a vector of ones, let's say you have ones, 1, 1, 1. Let's say you have 3 data points. Okay, our gradient has another 3 data points. Okay, let's say it has 5, 7, 9. Okay, the dot product between these two is 1 by 5, which is 5, 1 by 7 plus 7 plus 1 by 9, 9. So the final product is a scalar that sums up our gradient. So what we need to do there, instead of creating a vector of ones and then performing the multiplication, we can go to the gradient and then sum across this axis, the rows, okay, which is the axis 0. Okay, so what we're going to do is we're gonna self bias minus equal 0.01 multiplied by the np dot sum of gradient along the 0 axis. Okay, that is all we have to do here. I think with that we are actually done. Let's run it quickly, and this is no problem here. Let's calculate our loss is equal to criterion dot forward of z out, and it takes labels. Okay, let's see what loss looks like. That's our loss, and then let's try to back backpropagate it. Did we finish the backprop? We didn't. Let's go and implement it, okay? So this is going to be backwards. I'm going to fast forward it. Okay, so we left this out in the loss in the MSE. We shouldn't have a gradient. It doesn't take any gradient. Okay, let's now test it one more time. Okay, backward, missing one grad. Oh, okay. Let's run this whole thing again. Model.backward. I thought I did fix it. Gradient. Oh, the model itself. Oh, sorry. This one does need to take a gradient. And it did work. So I'm going to quickly build a training loop and then come back to you. Okay, and it worked. So what we did here is we specified 2000 iterations or epochs. Okay, and we started with the output. So we started with Z out, which is model.forward. This goes here in the forward. It puts the input through the network and then they pass to one another. Okay, and it gives us our output. And after that, we calculated the loss, and then we calculated the gradient from the same loss criterion. And then we took that gradient and we passed it back to our model in the backward method. And that method, all it does is it goes through the layers and it updates those that need to be updated. And we did that over 2000 iterations. And now we have a gradual decrease in loss. Let's have a look at our outputs. Remember, we designed it to be a parabola. So our predictions are, let's actually print our y. Let's just do it here. Okay. So we have very close to 9, very close to 4, very close to 1, very close to 0, not too close. Can take more iterations maybe if you're trying to overfit it. But yeah, you could see it is actually predicting them accurately. So if we run it for another, say 4,000, okay. Obviously you don't want to do that. We are just playing here. It's a toy data set, okay. Normally you don't want to overfit to your data, but not to this one. This is too small. Okay, so that is our network. It's super duper. Let's go crazy with the numbers. I want to get exact numbers. Yeah, super close, super close. All right, and that's it. So this is a silly data set. I'm going to prepare a much more complex data set, and then I'm going to show you how actually it learns. All right, I'll be back. So this is the data set that I prepared. It's a two sinusoidal data sets. One of them is modulated, the other one is intact, and that I spliced together. And we have 600 data points. I trained our network on 700 plus 1 million steps. It took about 45 minutes to finish. And this is how it managed to fit to our complex shape. So let's have a look, see how it fits slowly, starts to fits through the different shapes. And yeah, so within, let's say, within 1 million steps, it was almost converging. And beyond that, yeah, it didn't do much. Anyway, so this is a demonstration of how to implement a neural network from scratch. You can use this very network, to implement much more real-life data sets, to use it with real-life data sets. I wouldn't advise you to use it because we have better frameworks like PyTorch or TensorFlow that are much more appropriate. They have better optimizers, they better initializations and regularizations, different kinds of regularizations. But it's always good to have a feel of how these algorithms are implemented so that you can understand, even when you go and use them, it is always better to understand what's happening underneath, under the hood. Anyway, thank you. That's been it. I hope you found something useful out of this, and I hope you can now implement a neural network from scratch.